Well, you see the title at the top there gives you an idea as to what this handout's going to be all about. We're again going to talk about random effects, and now we have 2 random factors instead of 1. So we're going to up the game 1 notch. I should mention that, we had an earlier handout about, what did I call it, probably 2-factor ANOVA. And so we talked about the ANOVA table when we had 2 factors, A and B. There would be an extension of that. What if you have 3 factors? What if you have 4 factors, and so forth? Well, basically, I don't have any separate handouts for those kind of problems, but I would just sort of tell you, well, do the obvious things. There's no major changes or surprises if you have 3 factors. And so we'll run across examples of that as we go along a little further. But for the moment, I'll just make that little comment. So with this one here, we have 2 random factors. Well, if we had 3 random factors or 4 random factors, we would be doing something similar to this. Anyway, let's look at what's here. So here's a view of the data again right here, where we have factor A has levels 1 through little a, factor B has levels 1 through little b, and then there's a cell, say in the ith row, jth column, where we have n observations. So they're called y, I, j, k. So this is the kind of data set that we have. We can deal with a table of cell means. And so here it is right here. I don't think we need that far. Notice the dot notation is being used here again as before. And we have, I look at this and I see there's an error. That should not be a bar. That should not be a bar. So throw those bars away, because those are just totals. And then the means are over here with the bar on top. So here's some of our starting looks at the data. Now we're going to look at a model equation for this type of a problem. And there you see it written in this form. The mean in the ij cell is called uij. But that is broken down into component parts this way, where we now talk about an overall mean mu, a row effect alpha I, column effect beta j, and an interaction effect alpha beta ij. So these pieces in the model are all random variables. So the alpha i's are normal, the beta j's are normal, the alpha beta ij's are normal, and the eij error terms are also normal. So notice that all pieces of the model, except for the mu, are random variables. The classical model is to assume they have normal distributions, so we'll do that here as well. And so this is what's going on for our model equation. Now we have sums of squares, which should look just like sums of squares that we had before in the fixed effects case. There's no change in these formulas. So we have a sum of squares total, same formula as before. Sum of squares treatment. Treatment means the combination of both A and B together. That's the same formula as before. And sum of squares error, same formula as before. and it just points out in the remark that we have this equality. Sum of squares total breaks down into sum of squares treatment plus sum of squares error, and there's their degrees of freedom. And now we further break down the sum of squares treatment. We define the sum of squares A, same as before. Sum of squares B, same as before. Sum of squares interaction AB, same formula as before. So I won't look at these formulas in any particular detail because they're exactly the same formulas that we encountered before. And then on top of page 3, it gives the breakdown. Sum of squares treatment breaks down into sum of squares A plus sum of squares B plus sum of squares AB. And then we have these two ANOVA tables. The first one is kind of the abbreviated one, which sometimes our software gives us directly. The second one is the more commonly used one with A, B, AB, error, total for the sources of variation. Now, the thing to notice about this ANOVA table is that there's some changes here from what you've seen before. Now, the changes start to come in. The sum of squares are the same. The degrees of freedom are the same. The mean squares are the same. But now things change in this F column. How do we get that? Well, here's the new column that we call the expected mean square column. So each of these mean squares had an expected value, and here's the results. For A, for B, for AB, for A. Now, if, for example, we wanted to test, let's see, I'm trying to look down below here a little bit. I wanted to test sigma squared AB equals 0. That is that particular random variable is constant. There's no variation in that random variable. I want to test that hypothesis. I look at this expected mean square column and I say, this piece then under H0 goes away. And so I find that I have two mean squares that have the same expectation sigma squared. This one and this one. So I form that ratio for the F statistic. Here it is right here. I take mean square AB divided by mean square error. And that's my F test then for this hypothesis. Now, moving on to another one, let's suppose we wanted to test this hypothesis, sigma squared A equals 0, so that the A random variable in the model has no variance. It's all constant. So that's our null hypothesis. So if I look at these expected mean squares, under that I would say, well, of course I'm always looking at mean square A as a starting point, right? So I'd say under that hypothesis, this piece is 0, so it drops away. And I'm looking at what's left, and I say I have to find some denominator that has that expected value. So I look in the list and I say, here's my candidate right there. So that forms my denominator. And so when I form the FA statistic, it's mean square A divided by mean square AB, not mean square error. So this is a difference from the fixed effects model as far as what's the proper F statistic. So anyway, guidance as to what's the proper ratio to use for the F statistic comes most conveniently from this expected mean square column. Right? Now, if I want to test the other one about sigma squared B being 0, I do the same kind of thinking. I say, start by focusing on b, the mean square b. If the h0 is true, this term is 0. So a proper denominator would be something that has this for its expected value. And there it is, mean square AB again, sitting at the bottom. And so you see that's the ratio that's formed here in the table for testing about B. All right, well, we'll look at an example where that's worked out very shortly here. But before we finish with this page, let's just look at the bottom here. If we wanted to turn to estimation, our goal is not to test hypotheses, but our goal is to estimate parameters. How do we estimate the parameters in this random effects model? That is the question. And here's the results down here. Sigma squared is estimated with mean square error. And that's because of this right here. Expected mean square error is sigma squared. Sigma squared AB is estimated with this difference divided by n. Now, to get our hands on that, our eye turns to this mean square AB, and there's its expected value. Now it doesn't estimate sigma squared AB directly. So the first thing I have to do is subtract off something which estimates this sigma squared. Right there, the mean square error. Okay. So that difference would have expectation n sigma squared AB. So I need to divide by n to correct that n. And so that's the formula that you see right here, dividing the difference by n. So that's how I estimate sigma squared AB. Now, if I want to estimate sigma squared A, I do the same kind of thinking, but I start with the expectation for mean square A, and I look at its expected value up here, and I say, I got to subtract off something to take this out. And so I look down below and I see that's the AB line, and so I subtract off mean square AB. Now that difference would have expectation. My lines are getting kind of tangled here, but it would have expectation in B sigma squared A. So I've got to divide by NB to correct that feature there, and so that's what we have there. And then the same kind of thinking is done for estimating sigma squared B, with that difference divided by A. So if we wanted to just estimate parameters, these four would be our estimates from the data of those four parameters. Okay. Let's see. Well, page 4, the top third is a proof. Let's take a look at that before we look at the data. So here it says sum of squares A divided by this messy expression here, En sigma squared A, n sigma squared AB, sigma squared, is chi-squared minus 1 times 3. That matches our ANOVA table line here, where it says that sum of squares A has degrees of freedom increase 1. So where does that come from? All right. So here's the formula repeated for sum of squares A. Now let's replace the y bars by what they're equal to in terms of the model parameters. So y bar I dot dot is equal to all this. Now you've got to go back and look at the model equation again, where it said that y I j k was mu plus alpha I plus beta j plus alpha beta ij, and then the error term, eijk. So if that's yijk, if I want to get my hands on y bar I dot dot, that says I have to average over j and k holding I fixed. So holding I fixed, average over j and k. And this is what I claim that I get. The mu is a constant in every term of that sum, so it just retains. The alpha I is the same because I is fixed. Beta, I write beta dot. And basically what I said here was that when I use a dot with a Greek symbol, I mean average. So I probably should have put a bar over the top of it, but I didn't. So there, that beta dot is the average of the beta j's. And then I have alpha beta I dot, averaging over the j. Then I have e I dot dot. Now the e isn't a Greek symbol. I probably should have a bar. It's the average of the eijk's over j and k, fixing I. Then for the other part, the y bar triple dot, when I do the same kind of thinking, I get this. So I'm canceling a few things, canceling the mu's there and there, canceling the beta dots there and there. I'm left with this minus that. Now this piece right here is kind of messy looking, but I just want to give it a single name, xi. It depends on the subscript I. I'm just going to call it xi. And if that's xi, then the average of those xi's is this thing over here. And we inspect the pieces, we see that it's so. So that's what I'm going to call x bar. And so when I'm looking at this messy expression here, trying to simplify its appearance, I say it's bn sum of I of xi minus x bar. Now what do I know about these xi's? Well, look at xi again. It's this messy thing right in here, but I know what kind of distribution this is going to have. What kind of distribution does this thing have? Well, these are all independent random variables that are normally distributed. So I've got to get a normal distribution out of that, a normal distribution out of that, and a normal distribution out of that. So let's see what's written here as far as the answer. Probably that EI should be an E bar. I would change that in that way for you. So the alpha i's have variance sigma squared A. Then the alpha beta I dots, remember that's an average over J. So that's got to have a variance like a sample average. There it is. And then the third piece in xi is this e bar I dot dot. That's also an average. And here's its variance. So adding up the three variances, I get this expression. Now what I'm trying to do here is to use the old result. If we have x's that are independent, and look at this formula looks like the formula for a sample variance of the x's. What kind of distribution does that creature have? Well, we did this in our very first handout, I believe. This has a chi-square distribution if you divide it by the appropriate sigma squared. And so here I put in the denominator the appropriate sigma squared, the variance of an xi. So this random variable by our old result is chi-squared with a minus 1 degrees of freedom. And then I just point out that, well, this formula that you're looking at here is the same. This formula here that you're looking at is the same as up here, line 1. So that's the improvement by this result. Then it lists some other results about distributions for the sums of squares in the random effects model. Number 2 is the parallel conclusion for factor B. So it's basically the same as 1, but just replace A by B. So that's number 2. We're going to have a proof that's very similar to the proof that I here to B. And then we have 4, distribution for some squares here. Now basically, having done this proof of 1, I'm saying, you check out the proofs of these other ones. See that you can feel confident in proving those results. All right, let's take a look at the example. So here's some data. It talks about a situation, breaking strength of synthetic fiber. 3 machine operators were selected from the usual workers. 4 machines were selected from the factory floor. And then using these 3 operators and these 4 machines, that gives me 12 cells. And I see right here. And what I have produced is 2 observations in each cell. So for instance, operator number 1 using machine 3, that resolves 108, 109. So I got 2 observations in that cell. Now, why is this a random effects kind of model? Well, there are many operators. I don't say how many. It could be a dozen, it could be 50, whatever. But there's a fairly large group of operators. I don't want to know an answer for the particular operators. I want to know an answer about operators generally. So I select 3 operators at random to use in the data. Then there's also many machines that can produce this fiber, and so I don't want to test all of the machines. That's too much work. So I select 4 machines at random from the population of machines. So there's many machines. From the operators, I had selected a sample of 3. From the machines, I had selected a sample of size 4. Okay, so to get the output, I used, as you see labeled here, the Minitab software, which I recommend to you because I'm going to start using Minitab software rather heavily rather than SAS. Okay, so anyway, here's the command lines to use in Minitab. GLM Y A V A times B specifies the model. Specify that factor A and factor B are both random with that subcommand. The brief 2 isn't important. That just controls how much output comes out. And then the last subcommand, EMS, says give me the expected mean squares. Okay. So now these are also available as menu choices. So if you're in Minitab, and you're in the menus up here for stat, for example, you can find designing experiments up there, and then when you choose 2 factors, something like that, you'll get a menu, and in the menu you can specify things like what's the model, which factors are random, if any. And so the expected mean square is kind of a checkbox. So if you're using the menu, this is all very convenient and easy to use. If you're typing line commands, these are the line commands that the program executed. So what did it produce? Well, there's some boilerplate summary information here. A is random with 3 levels, values. B is random with 4 levels, values. Then here's the ANOVA table. A, B, error, total. So there's some sums of squares. Well, Minitab is talking about sequential sums of squares and adjusted sums of squares. These adjectives in here. And in this kind of a problem, they're identical, so we don't have to think about the issue at all. But in some other kinds of problems, they do differ for some reasons, and we'll have to pay attention to that. But in this case, they're the same, so we don't have to worry about that issue. So there's some F statistics here, quick to look at, in corresponding p-values. Only the first one is significant. By the way, I'm not sure I remember saying this directly, but in this class, I'm always using alpha equal 0.05. And you should do the same in homework problems as well, unless it says to do something different. But otherwise, use alpha equal 0.05 as our class benchmark. So anyway, there's one significant result, the other 2 are not. Now let's stop and take a look here once. This F statistic for A, 10.77, comes from what ratio? Well, let's look back and say we should take mean square A, which is the 80.167, and divide it by mean square AB, 7.444, and I think, without checking this out with my calculator, it seems about right. You would get 10.77 with that ratio. So notice the program used the right denominator, is what I'm trying to say. It's using mean square A divided by mean square AB. To get the F statistic for the AB test down here, the 1.96, they should be taking 7.444, that's mean square AB, divided by mean square error, 3.792. And that's about right to come out with 1.96. So anyway, what I'm saying is that although these numbers just come automatically popping out in front of your eye, you should inspect them to make sure you see how they're following our formulas for the correct F tests. So that does check out. Then following the ANOVA table as its tests, there's a layout for expected mean squares, which I asked the program to do. So it gave me this kind of a layout right here. And it's supposed to be fairly self-explanatory if you look at this. Now remember what we're trying to point to here. Let me see if I can find that ANOVA table. What it's trying to do is to reproduce this expected mean square column. So you notice that there's sigma squares, sigma squared AB, sigma squared A, and so forth. But then there's these coefficients of N, NB, and so forth. So the program is going to be able to calculate those coefficients correctly when it finally produces, find it here. So these are labeled in this notation here. 1, 2, 3, 4. 1 for A, 2 for B, 3 for AB, 4 for error. So the 4 here means sigma squared. Then it has 2 times 3. And the 3 would be AB. Now the 2 is what we've called in our general notation, the N, the number of observations in each cell. We have 2 observations per cell in this data. So that's the N. Then over here, we have 1, which stands for sigma squared AB, sigma squared A, but we have this 8, and the 8 is going to be 2 times 4. 2 for the number of observations per cell, 4 for the number of columns. That's 8. And the 6 is 2 times 3. So anyway, all I'm saying is that you can check this Minitab output against the formulas that we had on an earlier page and see that it's doing things right. So these are the expected mean squares. Then it's going to give a little tableau telling us what error terms did it use for the F tests. For testing A, it used 7.44, which is the mean square for AB. For B, it used 7.44, which again is mean square AB. For testing AB, it used 3.79, which is mean square error. So that's sort of a redundant piece of information, but it's okay to have it there, it doesn't hurt. So now it's going to talk about estimating what they call variance components. So we have the list A, B, and error, And then we have these estimated values. Well, the first is an estimate of sigma squared A, then an estimate of sigma squared B, then an estimate of sigma squared AB, and finally an estimate of sigma squared. And so here's the results. Just list the four numbers there for us, and we can see the relative sizes of things, about which variance components are bigger or smaller than others. Now, starting at the very bottom of the page, it says, let's go back to our formulas. If we want to estimate sigma squared, we should use mean square error. So look at the table, 5.2.75. So there it is. And that's also right up here in this layout as well, right? If we want to estimate sigma squared AB, we should use this difference divided by n. So there's the two mean squares from the over table, divided by n, which is 2, and get an answer of 1.825. And there it is right there. And then estimate sigma squared A by that difference divided by Bn. There's the difference of B squares divided by Bn, which is 8. I get 9.09, which is this first value right here. So this layout right here, what I'm trying to point out, is consistent with our formulas, these, that we had earlier on the handout page. This is where and then on the top of page 6 is the final result for sigma squared B. And the thing to notice here is that the estimate for sigma squared B, as can sometimes happen, turns out to be a negative number. Well, we know that sigma squared B is a variance, so it can never be a negative number. So when it comes out negative like this, we just slide over and say 0. So I said equals 0 there is the thing to do when you get a negative estimate. Now sometimes we want these pieces of variance expressed as a proportion. So if I take the 4 variances, notice I've got a 0 in there for the negative one, right? Add them up, I get a total. Then say, of that total, what proportions are we looking at? So here's 909 over that sum. 61% of the variation is due to factor A. None is due to factor B. 12% is due to the interaction between A and B, and 25% or thereabouts is due to the random noise. So sometimes instead of the actual variance estimate, people like to look at these ratios. And they're easy to compute. You just have to know that's what I want. So no big problem to compute those if that's what's wanted. So there's a run through of an example showing you how Minitab handles a case where 2 random factors are involved in the experiment. Okay. I'm trying to regroup my thoughts here. Next, the handout is going to go on to talk about mixed models. Now we have 2 factors, again, A and B, where A is a fixed factor and B is a random factor. So we call this a mixed model. We had talked about earlier the case where both factors were fixed. Then we had talked about earlier in this handout, the case where both factors were random. And now here we're coming to what we call a mixed model, where one of the factors is fixed and the other is random. Okay, so let's see what it says about this mixed model. So the first thing it does is to write down the model equation. It looks the same as before, but we've got some changes. The alpha i's are fixed effects, and they have a side condition. The sum of the alpha i's is 0. The beta j's are normally distributed, like we had in the random effects model. And now we run into complication. We can have what's called an unrestricted model, where the interaction terms in the model are simply normal to some variables. Then there's the alternative to that, the so-called restricted model, where the assumption is that these interaction parameters have this distribution. Notice there's a coefficient in front of the sigma squared AB, which might be puzzling to say, what is that doing? Anyway, it's there. And these interaction variables, alpha betas, are not independent. So this line says the covariance between two alpha betas which have the same J but different I is given by that. And then the second line says the covariance between alpha beta which have both different i's and different j subscripts is 0. So we have independence there.
And I'm sorry, the i's, how do you interpret if j is not equal to j prime?
Let me think about what your question is here.
How to interpret?
Well, let's look at the first one. It says if I is not equal to I prime. Well, what I'm saying is that I want two different first subscripts, I and I prime, to be different. The second subscript is j in both cases. So if I was equal to I prime, then this variable is identically the same as this variable, and the covariance of a variable with itself is trivial, we don't care. Okay? So the only case of interest is when I is not equal to I prime. Then I look at the second line here, and I say, well, I want this covariance to be 0 so long as the j is different from the j prime. So the second subscripts be different is 0. So the second subscripts were the same. Then I'm back in this first case. So I don't have to say anything about that anymore. So this is very clumsy. I will agree to that. And there's yet more, because we have, these are random variables, so they have some covariances. Yet there's another condition coming up here about this.
So you say that the covariance between, say the second one, covariance between alpha, beta, ij is different than the covariance of the same row but different columns, so the covariance is 0. Between two different columns.
Different columns.
J.
Right there.
Yeah.
And then there's a third condition, which which is an arithmetic condition. The sum on I of alpha, beta, ij is 0 for every j. Now, my comments about this is, first of all, my comments are, the unrestricted model is clean and crisp. Just assume that all the variables in the model, the random ones, are normally distributed and independent, and that's the unrestricted model. No restrictions on the random variables in the model. The restricted model, as you see, has numerous conditions that are floating around, and I would call these technical conditions that we're not going to have to deal with. So, okay. But you'll find that the software, Minitab, for example, will refer to restricted model or unrestricted model. And so, what are appropriate F statistics to use depend on whether you're going to assume the unrestricted or the restricted model. To make things worse, if you look at other books on design of experiments, they talk about restricted models as well, but they put in different conditions than these. So this isn't the only set of restrictions that people have dealt with, statisticians have dealt with in this kind of mixed model. So there's numerous other kinds of conditions. And I didn't think it would be helpful here in this handout to try to list some other possibilities. Here's one sort of standard set of restrictions that is often used, and let's just leave it go with that without fussing about the point. But I think the main message is that mixed models are complicated because you've got to worry about what kind of assumptions are we making about the terms that are in the model. And it's just not a trivial thing. It can get kind of messy. So anyway, here for completeness, I've listed the assumptions about the restricted model, and there they are. So, now I wish this hadn't split across the bottom of the page here, but we start with an ANOVA table for the restricted model. So the first thing you see at the bottom of the page there is a line for A. Sum of squares, degrees of freedom, mean square, F statistic. Notice that the denominator is mean square AB. And then here's the expected mean square. And something changed here in the expected mean square column from what we had before, in that before we had in B sigma squared A. We don't have a sigma squared A because A is fixed, it's not a random factor. So there's no sigma squared A in our model. So what we have instead is this kind of sum of fi squared over A minus 1. This is like a variance of A for a fixed effect. But anyway, notice how that's different than what we had with A being random. Then we continue on and say, well, for B, there's my expected mean square. For AB, there's my expected mean square. For error, there's my expected mean square. Now, if I start to look at these expected mean squares to find out what's the appropriate denominator to use, notice that if I want to test AB is 0, then that drops out. And these two have the same expectation, so I should use mean square AB divided by mean square error. If I want to test sigma squared B equals 0, I'm looking at the line for mean squared B, and I say if H0 is true, that drops out. And then I'm left with sigma squared, so my denominator should be something whose expectation is just that, sigma squared. And I see it here, and so I use mean square error for the denominator there. So by fiddling with the expected mean squared column, I find the proper F ratios to use in the ANOVA table. And in SAS, here's a little tip that helps to get things to come out right. But my advice to you would be to always check by hand a couple of the SAS outputs so that you know that you told the program to do the right thing. Because it's very easy to make a mistake with this, get the wrong output, and then proceed on with the wrong answers from that point. So in SAS, this is a helpful thing to specify what's going on. For example, I think this is saying, if you want the hypothesis to be about factor A, use the error term, A-B interaction. I think that's what it's saying to do. And one could check out its little sample run with SAS and convince yourself that's what it did. Okay, anyway, let's go on. There's a little bit of general formula left here. This is tests and confidence intervals for pairwise differences on factor A. A is a fixed factor, so it makes sense to do things about it that we did for a fixed factor before. Namely, we could get confidence intervals for pairwise differences and other things as well. So here's the t-test. Take two sample means, divide by an appropriate denominator, and well, I won't do it right here, but you have to look back with our earlier formulas to convince yourself that's the right denominator to have for a t-test. Look back at our formulas to check that out. If you want SAS to do this for you and you're using proc GLM, do something like that. Again, you're telling SAS to use the error term to be the AD interaction. And then the confidence interval formula, instead of the t-test, is this standard looking thing here. And again, you see the 2 mean square AB over B is the standard error that we're using. If you're in SAS, use this kind of a line to help you out to get that kind of result. Okay, so here's an example. Let's take a look at this to finish up as a mixed effects data set. Okay, so we start here by saying we're growing tomatoes under a selection of soil types to study the effect of 3 fertilizers. So we have 3 fertilizers. This could be type of fertilizer, or it could be the amount of fertilizer that's applied, something like that. And then we have soil type, 1, 2, 3, 4, 5. So the fertilizer is a fixed effect. We only have 3 fertilizers that we want to test about. These 3 are not a random sample from some bigger population of fertilizers. They're just 3. Factor B, however, is viewed as random. We have these soil types are, the places where they planted the tomato plants, and that was just a random selection from the available land that we were working with. So B is random. So A is fixed and B is random.
Five different plots from a particular field. If you divided the field up into a grid, randomly selected 5 independent grids, maybe.
6, I guess, right? Am I reading your question right? For soil type 1, which would be some field, I need that. So I need to divide it up into some kind of grid where I have 6 portions. And then at random, I would select 2 of them for fertilizer 1, at random 2 of them for fertilizer 2, and so forth. All right, so let's see what happens here at this date. So the first thing I did in Minitab was just to produce some descriptive statistics, and that's this first layout here. C1 is where I had the response. And C2 is factor A. So describe C1, the response, semicolon, by C2 period, and it gives me this table of means and standard deviations. Okay, so that I may or may not want to use for other purposes. So now I'm using the ANOVA menu, Y, A, B, A times B for the model, random B. Notice I didn't say random A, I said random B. A is not random. Restrict says use the restricted model. Okay. And then EMS says give me the expected mean squares under this restricted model. So there's my input. And again, these choices are in the menu, which I find actually very convenient to use as well. But if you'd like to type line commands, there they are. So the first thing we see is the ANOVA table. And notice that we have 3 F statistics, and I said I typed this in myself. It has the correct denominator for F on A. Here's F on A. And what we should be doing with that one is to take mean square A and divide it by mean square AB, right? And so let's look here. So that would be 34.6 divided by 1.8. Looks like it comes out about that size. When it did the test on B, this F statistic here, it's got to use mean squared V over here. So that would be 9.4 divided by 3.6, which comes out to about 2 point something, so that's in the right ballpark. So anyway, my instructions to the program up here initially say that there's our model, B is random, and then of course A is not because I didn't say random A. So the ANOVA table has to calculate the correct F ratios, and it does. So check that out a little bit by some handwork to see that you're convinced of that as well. Now I ask it for expected mean squares, so here they come at the end of the line. So 4 is the error, so I have 4 in each line for the sigma squared. And then notice how we have something different coming out between the line for A and the line for B. They have a different pattern. And what's going on there is that the program is reminding us that for A, there's 3 terms. But then if you flip the page over to page 7, for B, there's 2 terms. For AB, there's 2 terms. And so that's showing up in the mini-tab expected mean squares as well. So these are the right coefficients. 2 is the n, 6 is the 3 times 2, and the 10 is the 5 times 2, and so forth. So it has the right coefficients in there as well. But again, you can check that out yourself by tracing back to our formulas. So on page 9, with that little comment there at the top, basically it says factor A is significant, but the other 2 are not. And it says we could do some follow-up confidence intervals about factor A, because factor A, the fertilizer type, is a fixed effect. So with 3 levels of fertilizer, we could form 3 pairwise differences, for example, and worry about confidence intervals and such for those 3 differences. So that's where the example ends, right there. So this handout then has talked about 2 random factors in a mixed model where one factor is fixed and the other is random. And it shows how do we do the f-tests for the various hypotheses we might want to test. The whole handout dealt with 2 factors, A and B. Well, what if we have 3 factors? If we have 3 factors, then all 3 can be random. Or one could be fixed and the other 2 random. Or 2 could be fixed and the third one random. And so things start to get much more complex when we have more than 2 factors. So I'll say, learn the basic principles from this case. And then you will just sort of, what should I say, fill in what you need for the case of more variables. So we'll try to deal with those kind of examples as we go on a little further. But for the moment, I'll just make that comment to say, watch out, we're going to have more complicated mixed models coming up. Okay? Let's stop there for today.